Hello. All of our Algebra 3 folks. It's been hectic jumping back into all the curriculum this week. Uh, Algebra 2 folks, I don't know. I don't know if we're going to make it to Algebra 2. They just, I see lots of puzzled looks on the face, and we're taking all of class trying to get through one lesson. It's like, we're not making it. We're not doing very well. Algebra 2 is going to get better. Going to get better. Drive me insane starting off here. But it's Algebra 3. It's going to be better. Algebra 3 moves at a pretty quick pace, but that's because you guys usually in great shape by this point. And we'll look at our lessons. We'll look at our lessons today, but I want to start off with how many sheets of paper are in a ream? Here's one sheet of paper. Here's a ream of paper. Some of you may actually know this because it is a standard unit of measurement. A ream is designated as this many pieces of paper. But if you don't know, you might be able to give a good estimate by looking at the picture there. But how many sheets of paper are in a ream of paper? Xander's got an answer. All right, everybody look at this photo and say that's got to be 500 sheets, Mr. Brock. It's got to be. Or you know what a ream of paper is, right? Let's look at this. A ream of paper is actually 500 sheets of paper. It tells you on the package if you have a ream somewhere. That is pretty standard, whether you get it at Walmart, Office Depot, Sam's, wherever you buy it. So let's take it one step further then. You go buy a full case of paper, a whole box. There's the ream of paper sitting next to the box. You can kind of see on top of the lid, it looks like this ream and another ream would fit side by side in the box. So how much paper are we getting now if we buy a whole box? I think they usually call that a case. Xander says, let's say 5K here, 5,000. They're saying probably 3,000. Yeah, the big question is how many of those reams will fit? Right? Jacob's going to go with 6. Lauren says 10 reams. So 10 times 500. So we got a few different guesses. Natalia's going to go with 5,000 and a case of paper, a box of paper. It's a lot of paper. We know that for sure. 5,000, 3,000. How many will fit inside there? Let's go take a look. 10 reams, 5,000. You see them sitting side by side there in the top of the box. Yes, there are 5,000 sheets of paper. We had guesses all around that, and several guesses of 5,000. And some of you may have just known because some of you know that. Let's try this one. People won't know this one. How many total cheese balls, which means all 6 of these added together? So you're sitting on the couch. You've got 6 buckets of cheese balls. You turn on the Netflix, open the first bucket, and have at it. How many cheese balls are you eating here? You're going to finish all 6 of them by the time you finish your Netflix binge. You're going to say, all right, Mr. Brock, I eaten them all. That's a lot of cheese balls. We know that. So if you look at it and kind of figure, okay, how many do I think is in one bucket? Then I'm going to have to multiply it by 6.
Which hospital you go to after eating 6 things?
I going to say, it might be another thing to figure out at the same time. First, figure out how many cheese balls you're eating, and then figure out what's the closest emergency room. My guess is if you finish these 6 cheese balls, you won't need a bathroom for about a week because you're going to be so constipated, I would think. I think that would cause a little digestion issue there. All right, I'm seeing 18,000, 4,500, 4,500, 1,800. We're all over the place with these cheese balls. All we know is there's a lot of cheese balls. And to be fair, he's not going to open it up and count them. We're going to go by serving size and how many servings are in there. 1,800, 3,000, 2,400. All right, we're a little bit further guessing on the cheese balls, but I kind of expected that. That's a little tougher. All right, let's take a look at our cheese balls. Let's see what we get to here. So they're saying 4,400. Hey, we had some folks real close. Xander said 4,500. Jacob says 4,500. Some of you guys are just right there on this. If one serving size of 1 ounce is 32 balls, so one cheese ball is 1/32 of an ounce. They don't weigh much. So if there's 32 in a serving and 23 servings, so if we do the math, because that's what they did there, 32 cheese balls in one serving, and there's 23 servings in the container. So one container has about 736 approximately. Notice in the answer up top, that's an approximate. That's not exactly, because you may get an extra cheese ball or two or be missing a cheese ball or two. And if we have 6 of these containers, that's where he gets the 44.16. 736 per container, and perhaps about 4,400. Oh, that's quite a Netflix binge right there. Let's do this one. How many staples are in a single strip? So my stapler's empty. I pull out a strip of staples, put them in there. How many staples have I got loaded up now? How many things can I staple? Staples in a single strip. We've all seen a staple. They're very, very skinny. It's not like this is 5 staples or anything. There's a lot more than 5. But one strip of staples, full size stapler. This fits all standard staplers. So we're talking about a standard size. So 210, 200, 200, 240, 220, 210, 125, 200-ish. I like the ish. That kind of covers us if we're, off a few. All right, let's look at this. And you guys are all over this one. A standard strip of staples does have 210, which a few of you guessed there, Daniel and Xander. Maybe you have some staples nearby that helped you, but maybe not. Because, looking at the size of those right there. So you know what our last question is then, right? If there's 210 in a strip of staples, how many is in the box? A box of staples gives us how many staples? We know there's 210 in each one of these strips. And we see that box, and looks like we can blow that up a little bit. Take a look at it. Better closer look at that box to see how they're kind of double stacked in there. And I'll tell you, they take the C shape and they stack them like this. They put them together. They don't just put them all back to back. So if you get a good look at that box and you think you're figure out how many's in there. They look like they're back facing opposite directions there.
The sponges only have the single layer of cells. These have 2 layers.
All right, I see 5,040. I see 2,500. I see 2,520. I see some math going on. Let's see what the box says. The box says 5,000 exactly. Now I think they're covering themselves because if there's 210 per strip, you can't get 5,000 exactly. The math doesn't work there. Because if we have 5,000 in the box and each strip has 210, we don't have an even number of strips. Now, I think there's 24 because it's 23.8. I think there's 24 in there. And if there's 24 in there, it is 5,040. But some attorney told them, hey, just put 5,000. So if some are broken off and it doesn't have 210, it's only got 208, we won't get sued. Hey, it said 5,040 on the box, and I got 5,033, so I'm going to sue you. You know, nobody's going to sue them if they get extra. So, but good job, everybody. All right, let's close that. We're going to look at our Algebra 3. Jump into this. We got a lot to go on. Now, I always recommend when you go to Buzz each week, the first time you go each week, go to the grade screen. Make sure that you're not missing anything, right? The only thing we had now was just this one assignment last week, which I'm pretty sure everybody in here has done. Good job. There's nobody in here. That's Algebra 3. Algebra 2 had still people missing this morning. You guys got them all. And we're going to do, 2 lessons a week. Well, there's a quiz next week, so that doesn't require and 2 lessons, and then the practice test and the test. So we're not going to spend on. This is a review of algebra, That's why we're going in 3 weeks. Going to be done with this, just a review. But we're going to start out with Algebra 1 review, revisiting functions. We're going to start back at the basics before we get heavy into our Algebra 3 stuff. But let's go back. Oh, I went too far. Let's go back and look at the first and second lessons and see how quickly we can get through this, because we've only got like an hour and 20 minutes. Algebra, order of operations. All right, a block foundation. Suppose you have a pile of blocks that are carefully balanced on top of each other. As such, now imagine holding one of those blocks down at the bottom, like that one right there. You say, I'm going to remove that block. Uh-oh, now look, my blocks are lying on the table there. Yeah, we've got blocks going everywhere. I keep pulling. Now this block's going. Yeah. So basically what we're saying is if we pull, if we don't have a good foundation, if we don't remember like our Algebra 1 stuff, even some Algebra 2 stuff, we're going to have trouble in Algebra 3. So that's why we're going to review here, just to make sure. How can order operations be used? How does order operations help solve 1 and 2 step? What procedures are required to solve equations with a variable on both sides? And when is it necessary to apply the distributive property? So hopefully we can go through this pretty quickly. Should be pretty simple for you Algebra 3 folks. Just going back and look at this. Here's more on the order of operations if you need it, but I think we can good this. Oh, no, let's look at this. John and Sam. I forgot it has this one. So they were given 12 plus 4 divided by 2. And John said 12 plus 4 divided by 2 is 8. Sam said 12 plus 4 divided by 2 is 14. Who is correct? John or Sam? Is it 8 or is it 14? If we take 12 plus 4 divided by 2. So John said, well, 12 plus 4 is 16 divided by 2 is 8. This is 12 plus 4 divided by 2 is 12 plus 2 is 14. Quick review here. Who is correct? Only one of them is correct because, it's all numbers. There's no guessing. People seem to be thinking that Sam's got it going together. Sam's got it going. No love for John here. All right, I know there's more than 3 people awake in this class. Come on, guys. Don't spend a long time on it. If you're not sure, just put a question mark in the chat. Just seeing how much we need to review this. Everyone seems to think it's Sam. Oh, you're right. It is Sam. Division comes before addition. So you have to divide the 4 by 2 before you add it to the 12. So it is 14. So, and we won't go through that. You can go, you have access to this. If you want to go back and make sure you remember what's first, second, third, fourth, fifth, sixth division, where's that? Where do you put that? Put there. And here's where they say which one solved correctly. We say Sam did. And they're like, good job. All right. So that's little order of operations. But we remember order of operations as PIMDOS. Maybe your teacher used, please excuse my dear Aunt Sally, to help remember that. Parentheses, exponents. So parentheses are first. Exponents are second. And then multiplication and division are equal, which means you do them from left to right. Do them from left to right. And addition and subtraction are equal, which means you also do those left to right if they're on the same line there. So remember, when simplified expression, always do multiplication, division, addition, subtraction, left to right. So here's some samples. We'll just look at one or two. 16 minus 4 plus 3 plus 10 divided by 2 times 5. Well, there's no parentheses. There's no exponents. So we go to multiplication division. So the first thing we do was divide 10 by 2, right? That's the first step. Oh, I just repeated everything. So 10 by 2 would be 5. That's the first step. So now we've got subtraction, addition, multiplication. So we got to do the 5 times 5 next to get 25. Now we have nothing but subtraction and addition. So we just do it from left to right. 16 minus 4, 12. 12 plus 3, 15. 15 plus 25. So we should end up with 40.
Do you not think like scooping up enough sand with it?
Expression, since there's no parentheses, simplify the exponent. 3 minus 5 times 4 squared. 4 squared is 4 times 4. Right? So it would be 3 minus 5 times 16. You multiply next. All right, you guys got this. Oh, this is an important thing to note, though. Negative 2 to the fourth power means negative 2, negative 2, negative 2. Here, let's actually start some notes on that. So if you got pencil and paper, negative 2 to the fourth, negative 2 to the fourth. These are not the same. This is negative 2 times negative 2 times negative 2 times negative 2, or 16. This is negative 1 times 2 times 2 times 2 times 2, or negative 16. Because the negative is not in the parentheses. So that means this is 2 to the fourth times a negative 1. Not the same. So that's important. That's primarily important when you're trying to do work on a calculator. If you're trying to take negative 2 to the fourth power on your calculator, let's see, negative 2. Oh, it doesn't let me do that. See, negative 2. Does it let me do that? Wonder how this calculator handle that. Yeah, negative 16. But if I'd done parentheses, close my parentheses and put it to the fourth power, I get a positive 16. So it makes a difference when you put that in the calculator. So that's why it's important to note that right there. And if you need more on order of operations, there's more samples in there. So simplify that. We'll move on because we know order of operations. Solving one-step and two-step equations. Then, again, I don't think there's going to be an issue on doing any of this. We'll look at like one sample. X plus 4 equals negative 7. So it's x minus 5 equals 3. These are all videos. 4x equals 12. X minus 8. Let's look at a couple of the trickier ones. I'm not, they got the x minus 4 equals 7. I know you guys can do that. You've been doing that for years. X equals 11, right? But let's refresh our mind on this. If we have the square root of x equals 5, we don't do this as often. So if we want to solve for x here, the opposite function of square root is squaring. So if we square a square root, this just equals x equals 25. So that's worth reviewing. Just remember, if we have a square root, we square it. That's how we get rid of the square root. Because that'd be the square root of x times the square root of x, which is x. And this is worth reviewing. If we have x divided by 8 equals 3, we have to multiply by 8 on both sides. X equals 24. So if you struggle with any of those, we'll put that there just as a nice reminder. For square roots and for if you have a fraction. You just multiply by whatever's on the bottom of the fraction. Fraction goes away. Multiply by what's on bottom goes away. So we don't have to spend a lot of time reviewing that. But if you need to review any of those, and there's a squared, x squared equals 81, you've got little videos that are 16 seconds long. So 16 seconds long. and this is probably not much longer, 10 seconds. So since you have these videos, I won't show these in class. Let's not take the time to do that. They're just one-step equations that you've been doing for years. Two-step equations, 3x plus 9 equals 30. We'll throw that one on our notes real quick just to refresh. 3x plus 9 equals 30. Two steps just mean first we got to move the 9. That's our first step. So we have 3x equals 21. And then the second step is just dividing by 3. So x equals 7. Again, we're reviewing. I think you guys can handle these 3x plus 9 equals 30. But if there's one of these that messes you up, sometimes we go through that and it's like, Mr. Brock, I never really understood this part. Please stop me. Don't let me blow through something that we really do need to take a moment to review it. I just don't want to waste a lot of class time if you guys are like, oh, yeah, I've got that nailed. But again, especially when there's videos here, x divided by 2 plus 1 equals 10. Oh, this might be worth watching just because it has a fraction and numbers that are not fractions. So let's review this one together just because it's worthy of our time. Of course, it has no sound. Okay. X divided by 2 plus 1 equals 10. So to isolate the variable and solve this equation, by subtracting 1 from both sides. Get the fraction by itself. Get the fraction by itself. Right? Get the x by itself. First thing we want to do is move the 1. So subtract 1 from both sides. Now it gets a lot simpler. We've got x divided by 2 on the left side of the equal sign, and we've got 9 on the right side. So since this is dividing, to get rid of a fraction, you multiply what's on the bottom. So multiply by 2, both sides. So we get x equals 18. X equals 18. So if we look at the original equation, 18 divided by 2, 9. 18 divided by 2 is 9. Plus 1 would be 10. So fractions, I know sometimes make us go, oh, wait a minute, this is a fraction. But remember, fractions are easy to get rid of. Just move everything to the other side, multiply both sides by the denominator. So here's more examples of two-step equations. 2x plus 4 minus 16 equals 10. Got to distribute. Remember, anytime we have parentheses, we distribute first. We got 2x plus 8 minus 16 equals 10. See, because we distribute that to get rid of the parentheses. So you got 2x minus 8 when you combine plus 8 minus 16. Move the 8, divide by 2. Again, x equals 9. So lots of samples in here. If there's any of these that mess you up, please go back and review these samples thoroughly because I want you to feel confident going into this year that, oh, yeah, I know all of that stuff. Let's look at variables on both sides. Just to review that, it's not real complicated.
7x minus 12 equals 5x. To solve this equation, the variable x should be on one side of the equation and the numerical values on the other. Begin by subtracting 7x from both sides. Simplify. Since negative 2 is being multiplied by x, perform the opposite operation and divide both sides by negative 2. Negative 12 divided by negative 2 is 6. Therefore, 6 equals x, or x equals 6. The solution may be written either way.
Right, yeah, and that shouldn't mess us up in Algebra 3. We're going to write it either way. Sometimes we get done to this point, and I'll just write x equals 6 instead of 6 equals x, even though the x is on the right, because we know these are the same thing. X equals 6 or 6 equals x. But that's just a nice review. Remember, if we got x's on both sides, we just got to put them on the same side. And again, you guys are Algebra 3. You've been doing this for several years. Not a big issue. Example 2, There's another video with distributed property. We'll go ahead and run that here. It's not going to take long either. Oh, this is another one that has no sound. Okay, never mind. Hold on. We just have to distribute the 5 and have to distribute the -2. And that will greatly simplify it because as we move forward, we're going to spend time talking about that. See, 5 times x, 5 times 2, -2 times 3x, -2 times -1. And then you just have the 3x at the end. So we just simplify all that. Combine like terms. 5x plus 10. You've got the -6x and the 3x. So it combines to -3x plus 2 because -2. Move the x's to one side. Move anything that's not an x to the other side. So there's a process of doing. So you got 8x equals -8. Divide by 8. And x equals -1. So I'm going to spend the 2.5 minutes. If they're not going to explain it to us, no sound on that one. All right, let's look at page 5. Like I said, this review should be bad. Practice problems. Oh, did we have a lesson summary at the bottom that I missed there? Oh, it is. Here's the lesson summary. Oh, we probably ought to look at literal equations. Lesson summary. Order of operations. They talk about that because we do that first. One-step equations like x plus 14 or 8x equals 14 or x over 6 or square root of x squared. 2 steps where you got to move something to the other side first and then divide by the coefficients. Variable on both sides, move it over. But let's talk about real quick like A equals LW because that sometimes we struggle a little bit on that kind of stuff. So when we talk about like A equals LW, what is that? Well, this is the formula for the area of a rectangle, right? This is area equals length times width. We should be able to, especially by Algebra 3, hopefully, rearrange this. What does W equal in this equation? Well, I've got L times W. So if I just want W, I just divide both sides by L. So W equals the area divided by the length. You just isolate the variable by itself. If we want to know, what the W equals, or what, let's see what other examples they give there. Oh yeah, this is a good one too. Area equals pi r squared. Right, so we're talking about a circle, the area of a circle. What does r equal? Well, that one's a little trickier. I need to get the r by itself. If I want to get the r by itself, I have to divide by pi first. I need to isolate it. So area divided by pi equals the radius squared. So get the r by itself. Then to get just r instead of r squared, I take the square root. So r equals the square root of the area divided by pi. Rearranging equations. Rearranging these equations to be able to pull out individual variables. So this is an important thing. So there we go. So that's worth a little bit of review on that because sometimes if we've got 4x squared, I don't want to square it. I don't want to make it terribly complicated. Minus 8y equals 20, and we want to know what is x. Well, we can't figure out a number for x without knowing what y is, but we can solve this for x by moving the y to the other side. So we got 4x equals 8y plus 20. Remember, we cannot combine these because this doesn't have a y. This is just a number. This is 8 times y. So it's 8 times y plus whatever the 20 is, so. Then to get x, we divide by 4. X equals 8y divided by 4 is 2y. 20 divided by 4 is 5. So this is what x equals. And sometimes we need that. We need to know what x would be, and we can find what y is in this by substituting this into an equation now, and perhaps solving something on there. I don't know if it's going to work substituting back into the same equation. Generally, you'd have like a system of equations type thing, but we need to sometimes figure out what x equals. So that is what this is talking about right here on literal equations. Being able to solve equations is a great skill to have. Solve literal equations is a fancy way to say we rewrite the formula. So area equals length times width. So here it is. Width equals the area divided by the length. So that kind of stuff. C equals pi times the diameter. If we want to know what the diameter is, we take C and divide it by pi. Same thing. And there's the R right there. So our lesson summary. That's not bad. Review of this. Match each expression on the left with its corresponding expression on the right. It's just, if you need the practice, and I'm not sure that you do, I'm not saying that you do, you may or may not. You just click on this and the corresponding answer over here. Parentheses, 10 divided by 2 plus 3. Well, simplify the parentheses, that makes it a 5 plus 3. So this one, if I click on that and click on 8, they go away because those match. We have an exponent first, 16. Then we have multiplication. Got to do that next, 14. 16 plus 14 minus 3. 27. They go away. So, there's more practice ones here. If you think you need that, if negative 2x equals 14, what does x equal? Well, it should equal negative 7, right? Because we divide both sides by negative 2. And then they show you how to do it. It doesn't say how many there are next. Yeah, there's 2 of 6. There's 6 problems there. Again, you may not need to do these, but they're there. Negative 6x minus 10. Oh, 2 steps. 2 variables on both sides. Move it over. Subtract x, 5x. Move this over. 5x equals 10. So x equals 2. Yay, awesome job. And how many is there? There's 5 problems there. Let's look at our first assignment. It's a review assignment. Google Meet's been doing something a little weird with some of this on there. So, all right. Yeah, there's just solving. Solving with a fraction. Solve a 2-step. Another 2-step. Oh, the first step is to do what for this equation? X on both sides. X on both sides with parentheses. What are the steps that you do to solve this? So you don't have to solve it, just what are the steps? Let's see. Steve and Aaron solved the same equation. Which one's right? We got 2 different answers. Oh, it's not just which one's right. Who made the error and what did they do that's wrong? I like that even better. What was the mistake? Where did they goof up? Because they got 2 different answers. Shouldn't have 2 different answers for this equation. And number 9. Okay, so this only has 9 questions. That's interesting. The formula of the area of a square is a equals s squared. Rearrange this to solve for s. So what does s equal if the area is side squared? So 9 problems, which means it's going to be weird because I think this is worth 25 points. So that's not a nice even number. If you miss one, you're going to have a weird score, right? Because 1/9 for 25 points, 8/9 of 25 is not a nice number. So I should add another problem or something where it's all 2.5. But I'll leave it at 9. That's how they have it. Could make it worth 27. Yes, I want to leave. All right, so that is the first lesson that we did. Like I say, Algebra 1 review, very quick and easy. Let's revisit functions because we're going to do a lot with functions this year. In his play Romeo and Juliet, William Shakespeare wrote, A rose by any other name would smell just as sweet. Well, in fact, roses do have another name. Scientifically, they're Rosacea, Rosadea, Rosa. So roses do have another name. How about that? So even you have different names, you have the full name, right? Which, may include your middle name when mom is mad, your full name. Your friends may call you by an entirely different name. You may have a nickname. So, a student by any other name is just as ornery or is just as smart, just as sweet, we'll say, right? Many of the equations you've been working with for years in math also have another name, but they are still just as sweet. All right, we're going to learn what are the different methods to identify functions, what processes are needed to solve them and their inverses, and how's the composition of functions related to the order of operations. Let's look at the second page here. Oh, this is a good one. I was talking about this in a class yesterday. Equations versus functions. Right? The math term function applies to some equations because, functions, there are many equations that are functions, but not every equation is a function. Not all equations have the requirements to be called a function. Just like not all plants are roses. Roses are plants, but not all plants are roses. Functions are equations, but not all equations are functions. So here's some equations that we may have encountered, and I'm sure we have. X squared plus y squared equals 1. That's the equation for a circle of radius 1, right? X plus 7 equals 10. That's a linear equation. Y equals 2x plus 3. That's a linear equation. Y equals x squared minus 7x plus 6. That's quadratic equation. That's a parabola. That's an up and down parabola. That one goes up, right? So those are things, oh, here's the table of them. So in order for an equation to be a function, there must be only one y for each x. So like the y equals 2x plus 3, for example. If we plug in the negative 2 for x, y equals negative 1. Because 2 times negative 2 is negative 4. And we add 3 to negative 4, we get negative 1. And so here are the values. So no doubt a linear equation is a function. If we look at a quadratic equation and do a table of that, negative 2 has 24, negative 1 has 14, 0 has 6. There's not two answers when I say x equals 1. There's only one, it's 0. There's only one y that attributes to that. 2 is negative 4. Now, I may end up with negative 1 being 14 and 2 being 14 or something, but that's fine. I can have two different x's share the same y. I'm just going to have two y's share one x. Let me look at this last one. That's talking about x plus 7 equals 10. The x squared plus y squared. This is a circle. A circle has a problem if we call it a function because while negative 1 works for this circle, there's only one y. When x is 1/2, there's two different y's associated with that. Square root of 3 over 2 and the negative square root of 3 over 2. We see that when we graph it, x squared plus y squared equals 1. Or if we want to make it bigger, equals 10. But like x right here, when x is 2, we got just under 2.45. And if we go to the bottom, we also have it. 2 has another y down here. So with circles, we see, all these x's have more than one y. This is not a function. Not a function. And with x plus 7 equals 10, in the graph of that, let me put it here as well. X plus 7 equals 10. It's a straight up and down line. There's only one x, but it has every y. Every y. There's a lot of y's associated with that. So this is not a function. It's linear, but it's a straight up and down linear, and it's not a function. That's the only linear equation that's not a function. It's one that's horizontal. So functions are great for graphing on the coordinate plane since they have one variable for the input, the domain, and another variable for the output, the range. So equations have multiple variables can be complicated to graph because there's so many inputs that affect the output. Like if you wanted to chart the growth of kudzu vines in Florida, whoo, man, I drove to Georgia this summer and I saw a lot of kudzu. There's multiple inputs to that. Average temperature, access to water that can affect the output, the growth of the vines. I mean, they can grow like a foot a day. Kudzu vines are crazy. They have taken over. They brought them over from overseas after World War II to control erosion because, they grow fast, so they'll keep the dirt in place. Well, they grow so fast, they've gotten out of control and they're invasive and they kill a lot of trees and everything else because you can't keep up with them, growing like a foot a day or more. In science, the X and Y variables are referred to as independent and dependent. So let's see. Here's a matching activity. Oh, I like this. Select a movie, then select the year that you think matches it. Okay, so let's look at Twilight. What year do you think Twilight came out? Basically, you got 2005, 6, 7, or 8. Natalia says 2008. I wonder if it matters which 2008 I select. I'm going to select the top one. Let's see if that's right. That is right. Natalia knows her Twilight. How about Madagascar, the original one? What do we think? Five, 6, 7, or 8. Mary's going to give us a guess. Thanks. Let's try that. Oh, that was incorrect. Okay, so Madagascar is not 2007. So do we think it was before or after that? Before or after Twilight? That's a good question. All right, we're going to try 6. I see a couple people saying 6. Daniel says 5, but let's try 6. Nope. Then we'll go with Daniel's 5. Yes, it was 2005. It was the oldest of these movies. Let's see. Pirates of the Caribbean, Dead Man's Chest. 6, 7, or 8. Dead Man's Chest. We'll try that 6. I see that. Oh, we got it. Xander, good job. See a few 6s on the screen. The Dark Knight. And then we got Enchanted left. So Dark Knight 8, it was. And then Enchanted 2007. All right, so there was the movies. Now, notice that each movie only had 1 year that was released. So that is a function. If we reversed this, we reversed it and said, okay, what movie came out in 2008? Well, there's more than one that came out in 2008. We had 2 movies that came out in 2008. So that would not be a function if we reversed it. We can only say what year the movie came out. That is a function. Because more than one movie comes out a year or movies wouldn't exist because you couldn't keep it in business. Notice the domain movie matches the range year. So that is the function. It's okay that 2 movies had the same 2008, but each movie itself only had 1 year, even if it had the same year for 2 different movies. It would not be a function if Madagascar was released in 2005 and 2007. We released it twice, 2 different years, because that would be 2 different ranges for one domain. It can be called a relation, but not a function. Right. All right. Page 3. The vertical line test. All right. So we talk about this in graphing. So if we have, let's go back to equation here, like y equals 2x squared plus 3x plus 2. All right. So here is a parabola. Right. We're familiar with a parabola. If we do the vertical line test, which means if we do x equals 1, and we want to say, we're going to take this all the way from -5 to 5. Okay, step 41. If we move that vertical line anywhere along that graph, it only touches the red line once. Even if I zoom out, it only touches the red line one time. So this passes the vertical line test. Right? There's nowhere that it touches the red line twice. So that's what they mean by the vertical line test. And I know this is review all the day. You guys know this. This is a nice refresher for if you've forgotten some of the little details. That's why we're going over the details. The vertical line test. So as we move a vertical line. So that's why when we had the circle, let's go back to the circle there. X squared plus y squared, and we're going to say equals 20 and make it a bigger circle. That vertical line is touching the twice over the red, up here and down here. In lots of places. It only has to touch it one place, does it touch it twice, and it makes it not a function. Just one time does it have to do that. Like over here, it's fine. It only touches one place right there on the edge. That's it. But when we move over, now it's blown. It's not a function anymore. And it's not a function for a lot of reasons for all these spots. But that is the vertical line test that's talking about in here. So like looking at 2x plus 3, connect that with a line, it's fine with the vertical line test because we put a vertical line on the left, put it on the right, anywhere along there, and it only touches it once. So this is a function. So that just tells us if you're really struggling, trying to determine if something's a function or not, graph it. Does it pass the vertical line test? You may say, okay, so I was looking at this quadratic equation. It was a little different. It was x squared equals y. Oh, let's see. No, it was x equals, not x squared. X equals y squared minus 2y minus 5. Well, it looks like a quadratic equation because it's got the squared, but it's a y squared. Wait a minute. That doesn't pass the vertical line test. Look at all this. Look where it touches it twice. Maybe you're looking at a weird one like x equals 2y to the third, and you're trying to figure out, wait a minute, let's see, minus 5y squared plus y. Oh, I didn't say plus y minus 2. You're like, this x to the third, I don't know if this is a function or not. Well, as soon as I graphed it, I can see, oh, no, it's not. I mean, it's fine over here, right? It only touches one place. But when I get in between this point and this point, now I've got a problem. There's 3 different y's for that x. And it could be that it's fine. Like there's a y to the third. That is a function. That one is a function because now it's fine. Nowhere do I touch the y twice. Every x only has 1. But as soon as it changes a little bit, starts getting more curvy, oh, now I've got a problem. Now I've got a problem. So you may need to graph it because it may not be real obvious by looking at the equation. It might be obvious, but it might not. But I can always throw it on a graph and then look to see, is there a point? Oh, yep, there's a point. There's a point where the x has more than one y. So don't let that fool you. The vertical line test is very useful. A quick way to see if something's a function. So determine which is a function, which is not by doing the vertical line test. Vertical line test. Very quick. We can say, oh yeah, that's a function. Submit. Yes. Next one. It's a function. It's a parabola, but it's a sideways parabola. Look, when x is 1, there's 2 different y's, not a function. So you can go through and quiz yourself here. Look, this is a linear function. I use the word function on purpose because, yeah, linear is function unless it goes straight up and down. It won't let me select function for some reason. Oh, yeah, I guess it did select it. It just didn't show me it was selected. How about this one? Oh, this is an absolute value function. It's not a function. It's just an absolute value equation. Circle, we've already looked at a circle. We know a circle is not a function. And here is an x to the third. This is a third power equation. Is it a function? Yeah. It flattens out and goes back up, but it doesn't have two y's anywhere on there. Function notation. We should just hit the review on that real quick. Function notation we will use from time to time because sometimes we need to designate. If we say y equals 2x plus 3, we can write that in function notation by substituting f of x for the y. These are the exact same equation. This is y equals, this is in function notation. Because if we find the inverse of it, the inverse is written as this, -1. This is inverse. And we really don't have a way to do y equals and tell you that this is an inverse. So we use function notation so we can write the function inverse. Also, we use function notation to say, for this equation, what is f of x when x equals -2? Well, that means we do f of -2 equals 2 times -2 plus 3. In function notation, it's real easy to say, okay, well, that means I'm finding f of -2. When the x is -2, I write it like this, and it equals 2 times -2 is -4 plus 3. It equals -1. That's what f of -2 equals. So this is a nice way to write that. This one you have to say y equals 2x plus 3 equals -1 when x equals -2. We can write it the same way right here. When x is -2, this function equals -1. Function notation. So just a little refresher on what that looks like. Function notation. F of x. All right, still more on function notation. What else do we got to look at? Let's see. Oh yeah, so that's kind of what I was talking about. If f of x equals x squared minus 8x plus 10, find f of 4. So that's saying if x equals -4, what is the value of this equation or this function? Quick and easy way to say it. F of 4. Find f of 4. So we just take anywhere there's an x in the equation, and we take this 4, and we substitute it in. So instead of x squared, we're looking for 4 squared. Instead of -8x, we're looking at -8 times 4. And of course, the plus 10 is still just plus 10. So then we evaluate it. 4 squared is 16, minus 8 times 4 plus 10. 16 minus -8 times 4 is minus 32, or minus 8 times 4 plus 10. Then we just do 16 minus 32 plus 10 is -6. Again, nice review. Let's look at domain and range. We haven't talked a whole lot about domain and range. Oh, that's a good one. I'm going to write that one down so we can put this in our notes. I like this. Find the range. Well, if we graph that, we say, oh yeah, well, the domain is all the x's and the range is all the y's. And we might be tempted to just go say, I'm just going to graph this equation. So the equation is y equals, which is the same as f of x equals, right? And on top is x minus 5, and it is all divided by 2. Oh, look, this is linear, so the range is -infinity to infinity, right? No, not for this problem. The range is not negative infinity to infinity, even though we graphed it and we looked at it and it looked linear. Because we've limited the domain. We said these are the only x's that are allowed. -1, 3, and 9. That's the only x's we're allowed. We are limiting the domain to 3 points. So the range, we got to take each domain. -1. F of -1 equals -1 minus 5 divided by 2. Substitute the -1. So that's -6 divided by 2, -3. So when x is -1, y is -3. So the range is -3. Now when x is 3, 3 minus 5 divided by 2. Again, just taking the x and substituting whatever we want x to be. -2 divided by 2. So that's -1. When x is 9, 9 minus 5 divided by 2, 4 divided by 2, 2. This is the answer. Find the range. The range is -3, -1, and 2. So when we talk about domain and range, we have to understand what the domain is before we can tell what the range is. In this case, just looking at the function, well, it's like, oh, that's linear. It goes forever. But we limited the domain. So pay attention to that anytime you work on a problem. What's the domain? Did they restrict the domain, or is the domain just whatever the function allows? There's a big difference. And if we want to check that at -1, we said the points were -1 and -3. That should be on our line. Yep, there it is. There is one of the points. We said another point was 3, -1. That point is right there. And then we also said 9,2 is on there. So if we solve this and those points are not on the line, we did something wrong. Because if we graph it, it does tell us something. It kind of lets us know where the points should lie. Because all 3 of those points should lie on the line of that equation. So graphing does help us just to figure out, did we do it right? Yes, we did it right. When x equals -1, the y is -3. That is on that same line. So graphing is a value for us as well. Just knowing, you got to know what you're looking at. Here's where they did it. F of -1, F of 3, F of 9, and got the range of -3, -1, 2, just like we had. So you just substitute it in there for domain and range. Page 4. Inverses. Yeah, let's say inverses, because that's something we don't spend a whole lot of time in our earlier years of high school. And probably need to do that. So an inverted roller coaster is a ride where the cars run underneath the track rather than above the track. Those are fun. I rode one in Cedar Point, Ohio. Cedar Park. It's pretty cool. An inverted airplane is an airplane that flies upside down. You may see that at some air shows. Inverting the colors of a photograph turns black colors white, white colors black, so it looks really weird because all the colors are inverted. So inversion is the process of reversing something. Reversing the order, reversing the position. You're switching things backwards of what you're used to seeing. So finding the inverse of an integer means performing an operation that'll cancel that number. Like if you're given 7, you can say, well, the inverse of 7 could be -7. Because if I put them together, it's 0. That could be the inverse. Or maybe you take the 7 and the reciprocal will be 1/7. Depends on what you're trying to accomplish with it. But there's more than one way to reverse something or to invert something. So 7 could be -7, 7 could be 1/7, different things. But with equations and consequently functions, finding the inverses requires reversing the variables and solving. So let's review that. I'm gonna do it in paper rather than watching the video, because you can watch their video. I'll let you, if you need to go back and review something. Okay, so let's go through the steps of the inverse, of finding the inverse. Step 1. Replace f of x with y. So we're going to replace this and make it a y. That's step 1. Replace f of x with y. So we're just swapping those. Swap those out. Step 2. Swap x and y. So this was a y, we'll make it an x. This is an x, we'll make it a y. So now instead of y equals 3x, we got x equals 3y minus 5. We don't do anything with the minus 5. Step 3. Solve for y. Well, we had it solved for y. Yeah, then we swapped it. So now we're going to solve it for y again, which means we've got to get y by itself. So we're going to move the 5 over. Now we've got x plus 5 equals 3y. So this is a 2-step equation, right? That's the first step. The second step is to divide. So it's one of the things where I'm going to swap it around. Y equals x plus 5 divided by 3. Even though when we solve it, it was the other way. Y was on the right, but it's the same thing. We know that. And then step 4. Replace y with inverse function notation. So the inverse of the original function is x plus 5 divided by 3. So there is the inverse of the original function. That's the 4 steps. I'll leave it up there for a moment if anyone's putting that in their notes. You may have remembered that because you've done it a bit in Algebra 2. I don't know if you did in Algebra 1 or not, but we did a little bit in Algebra 2, and we've had a whole summer since then. I do want to look at the graphs of these 2 equations. Take all this off. So y equals 3x plus 5. Oh, minus 5. Minus 5. Okay, that was the first equation. And its inverse, we said, was, and in general, you always use y equals when graphing. X plus 5 divided by 3. Okay. The green is the original function. The purple is the inverse. The thing to note is, let's see, this point here, 3, 4. 3, 4 is a point on the original equation, which means the inverse is going to swap those. 3, 4, that means 4, 3 will be on the other line. Because when we solve the inverse, we swap the x and y, and the result of that is all the x's on this line become the y's on this line, and all the y's on that one become the x's on this. Where's another point? Looks like that point's on there. Yeah. So 4, 7 is on the original one, and 7, 4 is on the inverse. That's the cool thing about inverses. You can check those by graphing them as well. Did I do that right? Is that the inverse? Well, I can throw it on a graph and tell for sure, yes, I got it right, because the graph is correct. It is all a reflection over y equals x. All right, it's a reflection. That's going to be the same on both 2.5, 2.5. But it's a reflection over that line. And as long as it looks like a reflection of that line, and the points are working out 3, 4, 4, 3, 4, 7, 7, 4, I know I've done something right. This is correct. This is the inverse. So you can go through this video if you like. 1 minute, 7 seconds. And it shows that same graph reflected over that. And it talked about the points. If you have the point 0, -5, the inverse has -5, 0. If you have 1, -2, the inverse has -2, 1. So this one's a little trickier. F of x equals x squared, and we want to find the inverse. So let's do that one. Just because it deals with functions we don't play with as often. So first thing, make it y equals. Then replace the y's and x's, swap those. Solve for y, square root. So y equals the square root of x. So the inverse equals the square root of x. So that is the inverse of x squared. So get a little fat there. Let's put that on a graph and look at x squared and the square root of x. And this is one where the domain may come into play as far as all that goes. Let's see, y equals x squared and y equals square root x. This is where the domain comes into play. Because the square root of x is only a function if we limit, if we limit the domain of this, because it would also have the negative values, but then it's not a function. It's not a function. The square root of x, well, there's not a square root of a negative value, right? So that's why it stops at 0. But we know the square root of 4 is 2 and -2. So it would not be a function if we graph the bottom part of it. So this limits to where it's only positive values of y. We only look at the positive values. Let's see what they do with that in the lesson. Switch the variables, solve, replace with the inverse, and the graph. Does it pass? Oh, they graph the whole thing. Desmos did not graph the whole thing. It only showed the positive values. It didn't show the negative values. So if you graph it as it should be, plus or so that's how you do it. Plus or minus. See, do they have that symbol that I can use down here? See the plus or minus. And maybe if I just type plus minus. Oh, no. You have to graph them separately on Desmos. The positive square root of x and y equals a negative square root of x to get the whole thing. So there it is. X squared is a function. The inverse of x squared is not a function. Like I said, we know 2 and -2 are both the square root of 4. So to graph it, it is not a function. So sometimes the inverse is not a function, even though you took the inverse of a function. Well, those little details to pay attention to. Inverse functions can be solved for a specific x value, just like any other function. So if you have f of x equals 6x plus 2, replace it with y, reverse the x and y, swap places, solve it for y, you get, y equals x minus 2 over 6, change it to function notation, and then you could say, if x equals 2, in the inverse, we can just put 2 in the inverse function and simplify 0 over 6. It equals 0 when x equals 2. So we can do f of 2 or f inverse of 2, either one. And, there'll probably be different answers because the inverse is a different graph than the original. But remember, not every function has an inverse that's a function. Like we looked at with the square root of x with the x plus 2. But if we restrict the domain of the original function, we can create an invertible function. If we said, okay, I'm only looking where, let's see how to do that in Desmos. X is greater or equal to 0. If I restrict the domain and I say, for y equals x squared, when x is greater than or equal to 0, then the inverse is only the positive side of square root of x. And now the inverse is a function of the original equation. But I had to restrict the domain to only talk about the x is greater than 0. So there you go. The domain, if you restrict the domain of f of x equals x squared to numbers greater than or equal to 0 only, then the inverse will have only positive values, and it becomes a function. All right, page 5. Composition of functions. This messes people up a little bit, so we're going to play with this a little bit. Jaden is saving money to buy a car. If he can earn $1,500 more, then his parents are considering tripling the amount that he has in his savings account because he does so well in school last year. So is it in Jaden's best interest to earn the $1,500 now or wait until his parents triple his savings? All right, so let's look at the two functions. Get another sheet of paper here, and we'll write these out, and we'll do the math to see when should he do this. So f of x equals whatever money he has now plus $1,500. G of x would be 3 times the money he has in the savings account. So looking at this, we can do this 2 different ways, right? So this is the amount of money in his bank account, and if he adds the $1,500 in there, this is his parents taking whatever's in his bank account and tripling it. So if we do f of g of x, that's saying his parents are going to triple it, and then he's going to add the $1,500. F of g of x. When we have f of x, that just means if we check f of 2, that means we're substituting 2 in for x. If we have g of x there, that means we're substituting g of x in for x. So if this is g of x, then the equation is 3x, because we substituted this in. That's why I'm putting this around. This used to be x. Now it's 3x, because that's what g of x is, plus 1,500. Right? So that's what this equation equals. 3 of x, there's no simplification to do. Parentheses I just put to emphasize. If we do it the other way around, what if his parents wait till he makes $1,500 more? Now we're doing this equation, 3 times, but instead of x, I'm substituting f of x in there. See, this is the same equation, g of x, but instead of x, I'm substituting this equation into that, which equals 3x plus 4,500. So this one equals 3x plus 1,500. This one in there. So he should put his $1,500 in there first before his parents triple his money, because then the 1,500 will get tripled, because it'll end up with this much money if he puts his money in first. Earn now. This one is to wait. Let his parents triple it, and then he earns his $1,500. This one says, let's put the $1,500 now. Earn 1,500 now, then let the parents triple it. But that's how we do the composition of functions. You substitute one function into another function. So, see, if his parents triple his savings first, and then he earns another 1,500, you end up with the 3x plus 1,500. Right? But let's say he begins with $1,000 in bank. So here's a testing of it. So the one way, 3x plus 4,500. That's if he puts in the money now. 3 times 1,000 plus 4,500. He'll have $7,500 if he goes ahead and puts his $1,500 in there. If he waits until his parents triple it, 3 times 1,000, now they'll put in 3,000. Another $3,000, and then he adds 1,500. He'll only have $4,500. So that makes sense. Go ahead and earn the 1,500 now and put that in there, and then let his parents triple his bank account. So he'd be wise to earn the $1,500 before his parents decide to triple it. Thank you, Mom and Dad. F of x equals 7x, g of x equals 3x plus 10. Find f of g of x. Substitute it in. So g of x goes inside the f of x. So you've got 7 times 3x plus 10, because 7x became 3x plus 10. And then you simplify that. 21x plus 7. Here's one. Let's do this one. We still got a few minutes. Okay, here's what the problem says. It says, here's f of x. 10x minus 3. Here's g of x, x plus 6. Find g of f of negative 1. Okay, you really have 2 different ways to do this. First, we can find out what f of negative 1 is. So if we did that and did it this way, we would take 10 times negative 1 minus 3. Negative 10 minus 3, negative 13. So we could do that. And so then this would become g of negative 13. Because that's what f of negative 1 equals. So then we just take negative 13 plus 6, and it equals negative 7. So that's what g of f of negative 1 equals. Negative 7. The other way we could do that is we could go ahead and substitute g of f of x. So instead of x, we'll put this equation, g of f of x, and say it's 10x minus 3, that's what x is, plus 6. So we substituted that in for the x. Then we can simplify this. This is 10x plus 3. Right? Minus 3 plus 6 be plus 3. So then we can, let's see, that's g of f of x. So once we have what g of f of x equals, then we could substitute the negative 1 in then. So 10 times negative 1 plus 3. This is negative 10 plus 3, negative 7. Either way, we'll get the same answer. Whether you find f of negative 1 first and then substitute that in the g of x, or you put the whole equation into g of x, simplify it, and then put the negative 1 in there. I'd just like to show you that it doesn't matter which way you do it. You should get the right answer either way, as long as you don't mess something up in there. But you can do it either way when you have this kind of problem. I personally like to go ahead and put negative 1 in and figure out, okay, f of negative 1 is just negative 13. So I'll just put negative 13 into g of x. I find that a little simpler. Depends on the equations. Sometimes with the equations, it may be easier to go the other direction. There's another thing there. If you want to verify it, you can graph it, or you can substitute it in. And when you substitute it in, you should always get x. If I substitute x, 3x minus 5 into the inverse, that's the inverse of the original, 3x minus 5 plus 5, it'll simplify down to x. lesson summary. Here's how you do the inverse. There's those 4 steps. Graphically, composition of functions. Right there, putting the f of x and the g of x or vice versa. Simplifying that. And let's see what else was up here. Operations on functions. We can add functions, subtract functions from each other. All right, let's close that. They do have a page of practice problems. You know, match each member of the domain with the corresponding member of the range. So if this is the equation, if the domain is -5, what is the y? Well, you just put -5 in for x in that equation. -5 squared is 25. -3 times -5 is 15, so it's 40 minus 7. So it should be 33. There you go. So you can do that practice problem. Let's look at the assignment for this one. And then I got one more thing I want to talk about before we get out of here. 6, 7, 8, 10 questions this time. 10 questions. Find the inverse. No, not the inverse. I'm sorry. Find f of -2, which means substitute -2 in there. Find f of -3. Find the inverse of this equation. Use those 4 steps to find the inverse of that equation. Find the inverse of this equation. Find f of g of 2. So you can either substitute 2 in, find the value and substitute that in, or combine them first. Find f of g of -1. Find f of g of x, so the actual equation, f of g of x. Solve the inverse when x equals 4. So first you got to find the inverse and then substitute 4 into it. Same thing with that. All right, so there's the assignments for this week. I do want to talk about one other thing, because you guys did the AB plus C. Everybody's got it done in here, so I thought this is worthy to take a moment. And let's talk about the AB plus C equals A times B plus C. So let me put the notes up there and I'll play that real quick. A lot of people had some really good answers on that. And you guys put some thought into it and got some good stuff. And a few people may have been a little confused on it, but this was the assignment we had last week. If this is true, which it is, that's our equal sign, A, B plus C, what numbers can we have? And some people said, oh, well, any number. Okay, let's say then, if A is 2, it's like B equals 5 and C can be 7. Just pick 3 numbers. So 2 times 5 plus 7, because A times B, so 2 times 5 plus 7 would equal 5 plus AC, 2 times 7. So let's see, 2 times 5 is 10 plus 7, so this is 17. 2 times 7 is 14, so okay, that doesn't work with just any number. It cannot be any number, because the first ones we just threw in there didn't work. But I saw some really good stuff where people said, well, if A is 1, then B and C can be anything. So we could pick 6 and 11. All right? Doesn't matter. I just picked 2 numbers. So 1 times 6 plus 11 is the same as B would be 6 plus AC, 1 times 11. Yeah, because we're multiplying by 1. So this is 6 plus 11, and this is 6 plus 11. Yeah, if A is 1, then it doesn't matter. So that was one of the solutions. Someone said if they're all the same number, but really all the same number is because it works because of this. If B equals C, A, any number. This is really the 2 cases. If A equals 1, then B, C can be any. if B equals C, if they're the same number, like these were not the same number, but A was 1. If they're in, let's say that B and C equals 4. Now let's just pick a number for A. Let's say A is 7. Just pick a number. 7 times B plus C equals B plus, oh yeah, because look, if B and C are the same number, we're multiplying A times the same number and adding it to the other one. 28 plus 4 equals 4 plus 28. So that was the big things. If we make A equal to 1, then B and C can be any number. If B and C are the same number, A can be any number. So then people said, well, it works if A equals B equals C, but this is really just an extension of this. Because B and C can be equal to each other and A can be anything, which means A could also be the same number that B and C are. So that's really an extension of that. And then I did have someone say, if they're all 0, which again is just an extension of this. They're all the same. If B equals C and they're both 0, then it's going to be 0 equals 0. But it is thinking outside the box because people generally don't think about 0 when they start discussing this. Was there any other thoughts I didn't cover right here that you guys had contributed? I don't remember exactly. I haven't go back and look at all of them this morning. But there's some good thoughts in there. And there's some good thinking because I'd like us to kind of have just something very vague and abstract about that. Just kind of think what works, because any number doesn't work. The first numbers I picked were not going to work. And you can pick a whole lot of other numbers that ain't going to work either. The only time it really works, if A is 1 or B equals C, or both, right? Yeah, if A equals 1 and B equals C, it doesn't matter because it already meets one of the 2 rules that seems to work all the time. So, but good job on that. I saw a lot of it. I expected Algebra 3. I knew there's going to be a lot of good answers. So you guys have put some thought into that and just kind of, okay, how is that going to work? That's how it works. All right, guys, we have class on Thursday. Well, I have class on Thursday. All of you guys, your grades are above 70%, so you don't have to be here Thursday unless you want to come see Mr. Brock. Say, hey, Mr. Brock, how's it going? Yeah. If you have a question about any of these assignments you're working on, I forgot how to do this, Mr. Brock. Can you help me? Come to class. I'll help you. Then you can go enjoy your day. I'll be here Thursday if anyone needs to come by. Otherwise, we'll see you in a week, next Tuesday.